Welcome to the third of our three-part introduction to sensing. In this lesson, we'll focus on sensor dynamics. If I perform an experiment similar to the experiments you've performed in lab, where I take a thermistor and I have that connected to something like a voltage divider, thus permitting me to identify a change in voltage based on a change in resistance. And let's say I take that thermistor and I dunk my thermistor in the ice cold water, and I take it out and then I dunk it in the boiling water, and I go back and forth repeatedly. What I'm effectively providing is an input signal that is a square wave, and that square wave is going in reality from 0 degrees C up to 100 degrees C, or as I've drawn it here, from some amplitude of 0 up to some amplitude, and let's say 2. So I start in the ice water at 0 degrees C, and then I put my thermistor into the boiling water. I go up towards 100 degrees C, back down, and I cycle through from the cold to the boiling water. In an ideal world, what we see coming off of the thermistor, off of our sensor, in a perfect world would perfectly match this square wave input. But what we see in the thermistor in the real world, it might look something like this. Say I start at some amplitude, let's call it 0.5, and it takes me a while, and I sort of gradually make my way up to, let's call it 1.2. And then with the thermistor back in the cold water, it sort of slowly makes its way back to 0.5, right? And this will repeat cyclically as the thermistor is dunked in the ice water and then the boiling water and back again. And so what I'm seeing off my sensor is not following the square wave, right? It has some sensor dynamics that describe the performance of that sensor in this environment, going from cold water to boiling water and back. And hopefully what you're seeing in red here, right, these dynamics, this is described by a first order system. Now, in 351 this semester, we're going to be thinking of sensors primarily as a linear system. And for a linear system, if I have an input signal, let's say that's capital F times cosine of omega t, and my output signal will have a cosine at the same frequency. There's a cosine omega t on the input and a cosine omega t on the output. But the amplitude has changed. So we had an input amplitude of F, and now we have an output amplitude, capital Y, of omega. So the output amplitude has changed, and in fact, it's dependent on the frequency. And then we've also imparted a phase, right? So we have a phi of omega as well. And the great thing about this is once I describe how my system behaves for, say, a step input or a sinusoidal input, I can actually describe the performance of the system for any input. So to understand the performance of our system, I'm going to think of my sensor in terms of a differential equation. And for a linear system, I can describe that mathematically then as a bunch of coefficients starting with a sub n, as well as a bunch of derivatives going all the way from the nth derivative down to the 0th derivative. So as we've written here, a sub n times the nth derivative plus all the way up to a naught times y, those are all equal to f of t. So the order of my system will be described by the highest order of n, the highest derivative that I need to accurately describe the performance of my system. So n will be my system order. Let's take a look at zero order sensors. A zero order sensor can be described by the following equation. So a naught, a sub 0 times y is equal to capital F of t. And here f of t is my input and y is my output. So I can rewrite this equation such that y is now equal to 1 over a naught times f of t, where I can think of 1 over a naught effectively as the sensitivity. So I can rewrite this as y equals k times f. And so k then is 1 over a naught, and that's the static sensitivity of this sensor. And we could think of the static sensitivity as really a proportionality between the input and the output at steady state. So what that means is if I have some input signal in blue, and let's call that a naught times u of t to denote that it is a step input, then my sensor signal is going to be proportional to that input. So perhaps my sensor signal has a amplitude a sub 1, and we are denoting that it is now a step response to that step input with the u of t. And so that A0 and A1, they're going to be related via this K, via this static sensitivity. The same thing happens if my input is now, say, a sinusoid. So I have a sinusoidal input, A0 times sine of omega t. I'm going to end up with an output that is proportional to my input. So I have an output, say, now defined as A1 times sine omega t. And so once again, A0 and A1, they're related by this static sensitivity. So the zero order sensor then, it's doing exactly what I want it to do, right? It's giving me a copy, let's say, of the input signal. It's just scaled by some static sensitivity.